All right, well, hello AP Physics students, and welcome to this video that's going to be going through problem solving, specifically problem solving related to work problems and work kinetic energy theorem problems. So this first problem is just relating to work. We have a 100-kilogram crate, and it's being pushed across the floor with some force F that makes an angle of 30 degrees below the horizontal. The coefficient of kinetic friction is 0.2, so we need to figure out what the magnitude of F needs to be so that the net work done by it and the force of friction is 0 joules. So here we're saying net work, which is equal to 0, is going to equal the work done by that applied force and the work done by the force of friction. Okay, so the best way that I think we should start this problem is just draw a free body diagram so we can see what's going on here. So we have force of gravity, we have our normal force, we have force of friction, and we also have our, oh, no, not there, we have our force applied, which is going this way, and it's at that 30-degree angle. Okay. So now what we need to do is we need to just draw this in terms of its components. So we have Fx here, and we also have Fy. Okay. So let's just start out, we'll start out in the y direction here. We'll do a summation of forces in our y direction. Because we know that the reason that we're starting out in the y direction is that because this applied force is directed downward, this normal force is actually going to be greater than our force of gravity. So we want to figure out what this normal force is, because we know that force of friction is equal to our coefficient of friction times our normal force. So we need to come up with an expression for our normal force. So that's why we're working in the y direction here. So a summation of force in the y is going to equal 0 because we're not accelerating in the y direction. We're just moving across the floor. So what do we have here? We have our normal force, and it's directed upwards, so it's positive. We have force of gravity, and then we also have this y component of that force applied, and that's also directed downward. Okay, so if we rearrange that, we're going to get our normal force is equal to Fg plus Fy. And now I'm going to extend this out and actually write an expression. So we're going to say that Fn is equal to mass times gravity plus F, and for y it would be sine of 30. Okay, so we need to keep this equation right here, this expression for normal force, we need to keep that in mind. Because now what we're going to do is we're going to work in the x direction. Now our summation of forces in the x direction is actually going to equal it's going to equal 0, because if our net work here is 0, okay, if our net work is 0, that means our velocity is not changing at all, so there's no acceleration. So that means our sum of forces in the x direction has to equal 0. Okay, so with that being said, in our x direction, all we have is Fx minus Ff. So therefore, Fx is going to equal Ff. And we know that Ff is equal to mu times our normal force. Okay, so now we're going to come down here, and I know that Fx is going to be the cosine of this. So I'm going to write that. I'm going to write F cosine of theta, which is 30 degrees, is equal to 0.2 times, now we can plug this guy in for our normal force here. So I'm going to write in times mg plus F sine of 30. Now notice here, we know mass, we know gravity, and we know, well, I plugged in the coefficient of friction. So we can now find what that magnitude of F needs to be. So I'm going to do a little math here. F cosine of 30, that's going to be, let's see here, what did I get? 0.866 F. And then we're going to have 0.2 times 980 newtons, that's our mass, times the acceleration due to gravity, plus F, plus 0.5 F, because the sine of 30 is 0.5, okay? So now doing a little bit more algebra here, we're still going to have 0.866 F, and now we're going to distribute that 0.2, so we're going to get 196 newtons plus 0.1 F. And now just solving for F, obviously we have to subtract this from both sides, so we're going to get 0.766 F is equal to 196 newtons, and then we are going to get F to equal 256 newtons. Okay, so big key in this problem was understanding that because our network was 0, there's no acceleration in our x direction, and that's why we were able to simply say that Fx was equal to Ff, because these two forces needed to sum to 0. Okay, so the next problem that I'm going to go through is a work and kinetic energy theorem problem. All right, so here's our work and kinetic energy theorem problem. So we have an itty-bitty flea here, and it springs itself straight upward. So starting from rest, then we know that the initial velocity of that flea is 0. And the flea then pushes off the ground. The ground exerts a force of 0.38 newtons on the flea, and then we know that that force does 2.4 times 10 to the negative 4 joules of work on the flea. So our job is going to be to find what the flea's speed is right when it leaves the ground, and then how far upward the flea moves while pushing off the ground. Okay, so to start here, I just want to list all the stuff that we know. So we know V initial is 0 meters per second because it's starting from rest. We know the mass of the flea, which is the 1.9 times 10 to the negative 4th kilograms. We also know what that force applied is. That's 0.38 newtons. And then finally, we know what the net work is, and that's 2.4 times 10 to the negative 4th joules. Okay, so for part A, we need to find what that final velocity is. So we need to find V final. Well, taking a look at what we know the network, we know the mass of the flea, and we know the initial velocity of the flea. So here we can directly use our work kinetic energy theorem. Okay, so we're going to say that work net is equal to the change in kinetic energy, which we can say is 1/2 mv final squared minus 1/2 mv initial squared. Well, we know that V initial here is 0, so this guy is just going to go away. So what we're going to have here then is work net is equal to 1/2 mv final squared. Now rearranging that to solve for V final, we're going to get V final is equal to 2 times our net work divided by the mass, and then we're going to take the square root of all that stuff. So if we plug and chug all that stuff, we're going to get a value of V final, which is 1.59 meters per second. Okay, so there's our V final. That's how fast that flea is going right when it's leaving the ground. Now part B, we need to find essentially the displacement of that flea while he's pushing off the ground. So I shouldn't use D. I did that in the last video. So we're basically looking for delta X. Well, what do we know? What do we know? We know the total network. We know the force that's applied. So here we can just use our work equation. So we can say that work net is equal to that force times delta X. And this is pretty basic here. Rearranging that, we're going to have delta X is equal to work net divided by force. Therefore, we're going to get a delta X value, which is oh boy, this is itty bitty, 0.64 times 10 to the negative fourth meters. Now, I could extend this problem out even further, and I could ask you how high the flea jumps. I didn't include that in this problem, but I could ask you a part C, how high does the flea actually jump? Like, where does he get to in the air? And I challenge you to do that on your own. But I hope that this video tutorial helped in terms of work and then work kinetic energy problems. Again, the big thing with the work kinetic energy problems is that we just always need to keep in mind that work net is equal to our change in KE. Okay, if we have negative work, we know that our kinetic energy is decreasing. If we have positive work, we know that our kinetic energy is increasing. So with that being said, take care, AP Physics students.